cores, and so you can run up to 160 threads in each node. These nodes have 512 gigabytes of RAM. It has 2 SSDs, okay, Micron SSDs, and it has 2 non-volatile memory, each one with 3.2 terabytes, okay, of capacity. Then in the same node we have 4 GPUs, NVIDIA Volta GPUs. They have 16 gigabytes of high bandwidth memory. And then we have a single port Mellanox network link, and we have the fiber link to the parallel system, which is GPFS. Okay, so just by looking at these specs, you already see that there are multiple storage levels. We have the GPFS, we have the DRAM, we have the SSDs, we have the non-volatile memories, we have the high bandwidth memory in the GPUs. So there are plenty of places where data is moving in these new configurations and new architectures that we are seeing emerging in the landscape of high-performance computing. And then the question is how do we use these multiple storage levels in a proper way? In this evaluation, we are mostly focused on the SSDs and the non-volatile memories and the parallel file system. We are currently doing some work with the high bandwidth memory of the GPUs, but I'm not going to present this work in this talk. So to show you a picture of the node, so that you can see, we have these are the 2 processors, the Power 9. And then you see 4 copper plugs, 1, 2, 3, 4 here. These are the 4 GPUs that are located in the nodes. And of course, as I mentioned, you have the DRAM, 512 gigabytes in total. And then we have on this corner, and we cannot see it in the image, here you plug the SSDs. You have 2 of those. And then the 2 bar boxes that you see here are the non-volatile memories that are available in each node. Okay. We did some basic performance measurements, and this is comparing the SSDs with the non-volatile memories. Okay, so what you see on the x-axis is the number of the nodes. Okay, and then in the y-axis is the bandwidth in megabytes per second. All right. You can see that on the top you have the SSDs, and on the bottom you have the non-volatile memories. And then in purple you see the write performance, and in green you see the read performance. You can see that the performance of the solid-state drives is much lower than that of the non-volatile memory. Here we're talking around 500 megabytes per second. In the case of the non-volatile memories, we are seeing up to 3,000 megabytes per second, so 3 gigabytes per second for writing, and over 5,000 megabytes per second for reading. Okay, but so this is something that we more or less expected. We already knew that non-volatile memories were supposed to have higher performance both on writing and on reading. However, what was interesting and was not very expected from this study was these drops in performance for the SSDs. And these were not one-time measurements. Each bar of this one is the average of 6 or 7 tests, and these were consistently low. So there were some SSDs in the system that were consistently performing bad. So in this case, for example, you see 350 megabytes instead of the 500 megabytes that you were supposed to get, that most of them get. So there are performance differences between the SSDs, okay? This might be related to aging, to the wear leveling strategies that I mentioned before, similar to the effects that were presented in the previous talk. When the hardware ages, it starts delivering bad performance until it completely fails. So if you have to write a checkpoint in thousands of nodes, it's quite likely that you will end up using one of these nodes that have lower performance. And the checkpoint cannot be assumed to be correct or to be reliable until everybody finishes writing. Okay? And therefore, if you simply compute that you should be able to finish writing in a certain amount of seconds because every SSD has 500 megabytes per second of performance, well, that will not be the case because not all the SSDs will perform at the best because of these reasons. All right? So this is something to take into account when you are using these devices. Now, this is a test that we did for analyzing the importance of the query depth. This means how many processors or how many concurrent writers are writing in the same device simultaneously. So you have the number of I/O operations per second in the y-axis, and you see in blue you have the SSDs, in green the non-volatile memory, and in purple the GPFS. So basically what you can see is that from the moment you reach 8 as query depth, the SSDs more or less still perform. It increases, the I/O operations increase as you increase the number of writers, but the difference is not as important as for the non-volatile memories. For the non-volatile memories, if you are using only 8 writers, then you will get a much lower performance than if you were using 64 writers, for instance. So depending on which devices you are using, the importance on how many writers you are using simultaneously have differences. There are some important differences there. Now this is the same for reading. If you look at this figure, the performance that you get with a query depth of 8 is completely different than what you will get with 128 for the non-volatile memory. And that difference is not as big for the SSDs and neither for the parallel file system. So these are just some examples that show that it's not as simple as believing I'm going to use non-volatile memory and everything will go fine. You have to pay attention to how you use them, how many writers you use, and different performance numbers that are important to take into account. So these are some of the complexities that arise when you are dealing with multiple storage levels. In this figure, what we measured was the importance of the transfer size while writing to each one of those different storage levels. So you have in the bottom the non-volatile memories, in the middle the SSDs, and on the top the parallel file system. And